Hi there, I'm Sanghvi, and today I'll be talking about ultrasound cavitation threshold detection in excised porcine lung tissue at 0.2, 0.5, and 1 MHz frequencies. A little bit about me is my name is Sanghvi. I'm a high school student at Homestead High School in Fort Wayne, Indiana, and I'm a recipient of the Charles Steger Global Scholarship Internship. The work is funded by a grant from the Focused Ultrasound Foundation through this internship program, and I participated in a summer internship at Sonicare Medical in Indianapolis, Indiana. I want to first extend a thank you to the Foundation for providing this grant and selecting me for the symposium, as well as Sonicare Medical for hosting me this summer. What about education? As a high school student, I didn't know too much about focused ultrasound, and as part of the Charles Steger program, I had to take a MOOC created by the University of Lyon in France that featured pioneers in focused ultrasound. It was quite helpful as it taught about the clinical applications of focused ultrasound, as well as the ins and outs of how it works and why it works. In addition, I received a lot of hands-on experience at the Sonicare Medical that taught me more about focused ultrasound, like the importance of degassed water and how to operate the machinery, as well as it taught me about the scientific method implemented in a true lab setting comparatively to the experience I had received in school. The motivation in the experimental plan. This was motivated by the current COVID-19 pandemic, which affects the respiratory system. The use of focused ultrasound is new and relatively unexplored for lung tissue. And this made me wonder how we can use focused ultrasound to treat obstructions, tissue, clots, and other lung issues. We know that cavitation is the main way that we can do that, and it can be sustained in other soft tissue areas, so I wondered at what point can it be sustained in the lungs. Therefore, my experimental plan was to identify the cavitation thresholds for different frequencies in lung tissue. We chose porcine lung tissue because it is close to human tissue, and we used 3 transducer frequencies, 1 MHz, 0.5 MHz, and 0.2 MHz. You can see those 3 transducers on the side in order from top to bottom. Experiment 1 was using the 1 MHz transducer. We obtained porcine lung tissue from the local farm, and the setup was shown below. We have the lung tissue placed in a glove, nitrile glove, with saline solution to imitate human tissue. That glove was sutured to a tissue holder and then held by a weight in a tank of degassed water. On the one side we have the hydrophone connected to a spectrum analyzer to collect the data, and on the other side we have the transducer that would treat the tissue. We firstly imaged the tissue before treatment, as you can see on the left image, and then we treated it at 3 different power levels, 0, 10, 15, and 38 watts. Half harmonics became visible at 15 watts, meaning that is where cavitation became sustained. In experiment 2, we used a 0.5 MHz transducer. The setup had to be changed to a manual setup, adding a function generator and amplifier to control the function and make sure that it was matched the frequency of the transducer. You can see the setup diagram here. The oscilloscope and the function generator amplifier were connected, as well as there was a resistor box to ensure that the correct frequencies in the transducer were all matched, as well as the spectrum analyzer and hydrophone remain the same. You can see that we changed it here. You see the imaging probe on one side and then the transducer on the other. We imaged the tissue again before testing it. Then we tested it at many benchmarks, and cavitation began at tap value of 17.4. You can see the half harmonics begin to appear in that second middle image. In experiment 3, we had the same setup as experiment 2. We again imaged the tissue before testing, as seen in the right image, and we tested at many power levels, and cavitation began at a tap value of 2.8 watts. You can see in the middle, that's where the half harmonics began. Tap testing, just to touch on this, total acoustic power testing measures the power in watts that energy is being delivered, and it allowed for a conversion between dial and standardized units. It had to be done for the 0.5 and 0.2 MHz transducers, and 1 MHz already had data. We used a tap meter, an oscilloscope, and a function generator. And as you can see in our 4 graphs, all of our graphs are relatively linear, which is a good sign. Cavitation thresholds for lung tissue. Here's the conclusion of our data. You can see that as the frequency changes, the cavitation threshold decreases. You see a slight increase between the 1 MHz and the 0.5 MHz transducer. We hypothesize that's because it went from a focused transducer to an unfocused transducer, and that can change the way that energy is delivered to the treatment site. However, you can see the difference between 1 and 0.2 MHz clearly, as it's a 15 watt and 2.8 watt and you can even look at the other mechanized indexes, pressure, and ISP as well. Finally, thank you again so much to the Foundation for the grant and for including me in the symposium. Thank you to Sonicare Medical for hosting me, and thank you so much for watching.